Okay. Welcome back to Astrophysics. We spent last time building your spectrometers that we probably won't use today. If you'd like to use your spectrometers, that would be great. You remember what they look like? They're these guys right here. But I also have some of these guys, which are spectrum glasses, which allow us to wear them, right? And we should be able to see everything we need to see. The trick is going to be measurement. And so I'm going to have to leave it up to you and to how we're going to measure these things. But you guys can figure that out. Oh, you need another pair. Tax dollars at work here. All right. I call these happy glasses because if you wear them, you make everybody else happy. Nice. There you go. All right. Oh, and let me give you one of these. Everyone's so quiet. It's the camera, isn't it? It's making you nervous. You don't want to be on camera. Well, too bad.
It's okay if you screw up, but none of us.
Yeah. Well, yeah, right. None of you want. Well, that's all right. At the bottom of this sheet, there's a waiver I need you to sign. There you go. Yes, it does. All right. So our goal today is to, well, let me give you a little bit of a background of what we're doing here, right? Spectra, stellar spectra, and spectra of any object are necessary because what's the only thing astronomers can really use to see things in the night sky?
Telescopes.
Telescopes, that's right. Telescopes that observe
Light.
Light, okay? So if we need to observe light, we need to know what the light is telling us, and the way we learn about what light is telling us is by breaking it up into its spectrum. And I think the last time I taught astrophysics, they told me that they thought it was the coolest thing ever because it meant that we get to study rainbows. Yeah? Get to study rainbows. No, that's physics. Physics is the study of unicorns. Astronomy is the study of rainbows. I did want to draw one thing down, though, on the board here, just to remind you of why we study astronomy, and to sort of remind you of the physics that we're going to need to do this. And I want to start with the periodic table of the elements. Can you see that okay? Okay. Just pretend the camera's not there. You're also quiet. I'm going to get rid of the camera if you're going to be like that. All right. So where are my chemistry students? What's after helium?
Lithium.
Wrong. Metals, yes. Sorry, you were being a chemist, yeah. This is the astronomer's periodic table, APT, which is different from ATP. The astronomer's periodic table. There's hydrogen, there's helium, and then there's metals. Now here's the really exciting thing about this, is that almost all of these things are very well described by a very simple model of the atom that does not require the knowledge of quantum mechanics. Another great reason to be an astronomer. Because the Bohr model deals with a nucleus and an electron, right? And in almost all cases you can approximate, if you're being very careful, you can approximate the spectrum of any of these gases by the outer electron going into different energy states. Now, that's not always true because some of the atoms get pretty complicated. For example, I'm going to be showing you neon, and I'm going to be showing you mercury. Those cannot be approximated by a single atom or a single nucleus surrounded by a single electron. But what is the composition of the universe? It's 90% by number helium and hydrogen, and 10% by number helium. And then everything else is to one significant figure, 0%. Right? So if we want to study the composition of stars, if we want to study the bulk properties of the universe, we really only need to understand hydrogen and helium. Now, stars do have other elements. Carbon, nitrogen, oxygen are some of the big ones, right? So you do need to know a little bit more. But to first order, to just start our discussion, we don't need to worry about that. We can just study these single electron atom. So we're going to use that as our model today. And I just want to write down the model as you probably remember it from your physics class. It is, the Bohr model says that the wavelength of light is equal to 91.16. Oh, sorry. Put my decimal in the wrong place. 911.6 times, this is for hydrogen, 1 over n prime squared minus 1 over n squared, n squared, near the edge there, in angstroms, which is 10 to the minus 10 meters. And what is n prime? Remember from your physics class, the Bohr model? N prime is the state that the electron drops down to. N is the state that it's dropping from. And so if I were to, let's see, can I just page over? How do I get a new page out of this? Add a page, there we go. So if I think about the energy levels of a hydrogen atom, I've got N here. This is 1, 2, 3, 4. The energy levels of hydrogen are equal to minus 13.6 times, or over n squared in electron volts. So we all remember, this is all review, right, for the most part, okay, from 2220. And that means that if I go from n to n prime, I'm going to release a photon. And if I go from n to n prime, that direction, I'm going to release a photon, which will that have, based on how I draw that, would that have a more energy or less energy than the first photon? It's just a camera. Just ignore it. We'll talk all the time in the other one. What if I've got a drop from here to here that releases a photon of a certain energy? This is energy on this scale, remember? Energy going up. Minus 13 electron volts at the bottom. So if I drop from here to here, I'm going to get some amount of energy. If I drop from here to here, do I get more or less energy? Less. Okay, so which photon is blue and which photon is red, comparatively? The blue photon has more energy, the red photon has less, right? So this is going to be a bluish photon, I mean comparatively, and this would be red. I'll put those in quotes because it's not really, they're not blue or red necessarily, just one has more energy than the other. Okay, so this is what we know happens in electrons. The question is, how do we use what we know about physics in astrophysics? And so what we're going to do today is analyze some of these spectra using this. Okay, so this is for Mike, because you just came in. All right, but before we start with the electron transitions, let's look at why things glow at all in the first place. So I've got an example here of a lamp that is going to glow, and it's some material that's going to emit light. Why does that material emit light when I put energy into it? Does anybody know? No? Anyone? Anybody know?
Wait, while you're putting light in a lamp, it's glowing?
Yeah, I'm putting energy into the lamp. Why does it glow?
Because it's heating up.
All right, because it's heating up. Excellent. Okay. Now, your book has a little bit more detailed description of what that means to heat up. So let's think about that for a second. When we heat something up, what do we do to the atoms? We excite, we vibrate them, and that they bounce together and they excite, right? So what is happening to the electrons in the atoms?
The electrons are moving to higher energy.
They're moving to higher energy states and then collapsing and emitting photons. Now, if you're not a dense solid, like a gas, or what we're going to show, like if we're a very rarefied gas, then you'll just see individual wavelengths from the individual transitions from the electrons, which is what you've learned in your physics class, right? That's the emission spectrum. But if you're a dense object, what's going to happen is those photons are going to hit other atoms and knock electrons around, or they're just going to cause the atoms to vibrate more if they don't have the proper transition, right? And so what's going to happen is you're going to get a population of states in different electron states in this atom that are always going to be exciting up and dropping down, exciting up and dropping down, and they're going to be doing that at a whole range of possible states and possible wavelengths, right? But all of that aggregated together gives you a spectrum of light coming out called the continuous spectrum. And that continuous spectrum, your book goes through a really nice derivation of where that comes from to get the Planck function, which is the black body function. And that function, which we're going to look at in a minute, is pretty important, that you can take an atomic structure of matter that has these very specific energy transition states, and if you do look at it in the aggregate of all the probabilities of all the states transitioning to one another, you get a glowing spectrum that depends on the temperature of the object. Okay? So that's the exciting thing about the atomic physics, is that you can get something that looks like a continuous spectrum from this atomic interaction. So now, what did I do with my glasses? Oh, here they are. So let's put on your glasses here. Let's do a little quick demonstration. Turn off the lights. What if I put glasses on here? Yeah, put on your glasses. Let's see if that works. Think that'll work? Maybe. So let's see what happens. Oh, it's totally going to work. Ah, so excited about this. All right. Let's turn this off here. Shutter this guy. Now I can't see anything. That's a problem. I'm on it. Be so much easier when we get the cyborg thing going. Okay, so I'm going to turn on this light. Oh, it totally works. Oh my gosh. I can see the spectrum on the camera. It works. All right. So this is a continuous light. I'm heating it up. I put on my glasses. What do I see? What's that? The whole rainbow. In fact, if I look really careful, not only see a whole rainbow, I see a double rainbow. Yeah, I see almost a triple rainbow. Double rainbow, triple. Anyway, sorry, that's several years ago. Okay. Rainbow on one side, rainbow on the other. Is it continuous? In other words, is every color present? Yeah, it looks like every color is present. Now watch what happens when I dim this thing down. Right? I'm going to dim this down. What color is present? Yeah, mostly red. There's a little bit of yellow, maybe a little bit of green, but mostly red. And that happens when I'm putting less energy in. This thing is much cooler. Right? If I crank this thing up, what's the first color that starts to come back? Red gets brighter, then green, then blue. Don't look directly at it. Right? Wow. Okay? And you'll notice that the blue gets much brighter. So as I'm heating this thing up, it's going from red to blue. Now what happens if I've got a material in the way of this thing is it's going to block out some of the light depending on the properties of the material. So let me grab some material here. Let's call this a bit of concentrated stellar atmosphere. It isn't really, it's a piece of glass called didymium. Vanadium oxide, isn't that right, Jessica? Do you remember what the chemical composition of this is? This is a filter. This is, have you ever seen those relaxation lamps? You know what I'm talking about? Those relaxation lamps. This is what they do. They put one of these filters in front of the lamp. But what this thing is here is this is going to block out. It looks like it's just a little bit darker, but it's going to block out part of the light. What part of the light is it going to block out is going to depend on the atoms that this stuff is made out of. So let me go ahead and do that for you. I've got a hot, dense object, and now I'm going to put this in front of it. Are you ready? Those people on the left, are you ready? Okay, what happens when I do this? Nothing. Okay, we should have a little discussion about enthusiasm for a moment. Okay? Enthusiasm is not a state of being, it is a state of readiness. Okay? You're enthusiastic in proportion to how enthusiastic you behave. For example, if I go to the needlepoint store with my mother, I can either go there and have a miserable 7 hours, or I can go there and be really excited about all the needlepoint stuff. And you know what? There's a lot of cool needlepoint stuff out there. And believe me, if you go into it being enthusiastic, then you enjoy the 7 hours in the needlepoint store with your mom. If you go into it kind of not really caring about needlepoint, it's a long 7 hours. What's that? Yeah, thank you. Yeah. Right. It's true, right? Enthusiastic is a state of readiness. So this is the coolest thing you have ever seen. Are you ready? All right, thank you. That was good, Nate. Thank you. I appreciate that. So I'm going to do it myself because I'm going to make sure this is working, and I see this. Wow! Holy cow! Right? That's cool. You ready? That's all right. Let's try over here. Are you ready?
Yes.
Okay. Isn't it? Yeah, and then you suddenly find out, hey, I am enthusiastic about this. That's pretty cool, okay? But it's not just dimming all the wavelengths. What is it doing? It's dimming very specific wavelengths, right? We call that an absorption spectrum because the electron structure, and actually in this case it's probably the rotational or the vibrational structure of this solid, is absorbing very particular wavelengths of light. Same thing happens in the star. If I put an atmosphere of hydrogen around a hot, dense core of a star, I'm going to get emission from hydrogen. Now, while we're doing that, let's go ahead and bring up the lights a little bit. There we go. Bring up the lights. So your eyes adjust faster. Let me do that. And then I'll do this. Okay. So now what I'd like you to do here is on your, in your activity, whoops, you can work in groups. Where's this? I have to give myself, okay. Whew. What I'd like you to do is look at these continuous spectra. Now I showed you these spectra with the black body spectrum on top, and I also showed you what absorption looks like. So when you look at these spectra, these are spectra of stars, you're seeing the absorption due to the materials in the atmosphere, and you're also seeing them overlaid on top of this continuous spectrum. So what I'd like you to do is take a minute to draw, and there's a little example here how to do it, draw the continuous contribution, the continuous spectrum contribution on these guys. So if and you have to be a little bit careful because you can't just follow the lines. You have to take into account the overall curve of this thing. So, for example, if I put, here's a spectrum, intensity versus wavelength, and I've got a spectrum that looks like this. Oh, you can't see that? Yeah. Okay. I've got a spectrum that looks like this. Right? The continuous spectrum is not going to follow that exactly. The continuous spectrum is going to go, it's some overall. Every single place you see a little divot is where stuff is getting blocked out by the atmosphere of the star due to whatever composition the star happens to have. Okay, so take a minute to draw. Go ahead and take this thing out. I'm collecting this, so we're handing this guy in. Take a minute to draw what the contribution is to that. And then once you've done that, after you fit your black body curve, see if you can compute for me the temperature of that star. Just simply based on where the peak of that thing is. And I've given you a relationship here that if you measure the wavelength in nanometers, then the temperature is equal to that in kelvins. And that's Wien's law. That comes from our black body spectrum. So take a minute to do that. And again, you can work in pairs.
So we're literally just drawing a best fit line.
Best fit line through there, taking into account the fact that there is a lot of absorption due to stuff, right? And while you're doing that, I'm going to do some stuff up here. Nice. All right. Now I know how to use that. That's good. All right, how are we doing? You have your curves drawn on there? Perfect. All right, you found your peak there. That's good. Ignoring all that scruff, excellent. Let's see what you got. Yeah, so yeah, this is going to get you the peak, but one thing you want to be careful of is this is a bunch of absorption, right? So it might just kind of tail off. And you'll get the experience. As you see more black body curves, more continuous curves, you'll get the experience with it. But that shouldn't affect your peak too much. That looks good. That looks good. All right. Are all these good, Jessica? Are there any I need to watch out for? Do we have temperatures yet?
You said this wavelength here?
Yeah. In nanometers. Should be nanometers. I am 99% sure. Should be nanometers. I just reformatted this activity so you guys are beta testing, but, you know, before I put it in production mode, you know, but yeah, I'm pretty sure it's in nanometers. Well, so rank it before you calculate it. See if you can guess based on the position of the peak, right? So we're practicing your intuition. What do you expect the answer to be? So I thought I was really not very good at writing on this thing, but I do awesome compared to, yeah, I'm not bad. I'm not bad. All right. Well, what is the ranking? Do you have a ranking for me already? Let's write that down. What's the ranking? Say that again. A. All right, we all agree on that? Okay. Now let's see if we agree on the temperatures. If we had what?
If we all just took acid before we came.
No, the problem is then the spectrum doesn't always go side to side. Sometimes it's, yeah. Now, and these aren't, they do make starburst glasses, which are like the spectrum, but they put patterns in them, which is pretty cool.
Yeah, those at Home Depot, they make like Christmas flake shape.
Yeah.
Yeah, a lot of Christmas lights on our house.
That's right. All right, what do we have for temperatures? Who's got a temperature for A for me? What is it, Mike?
I got about 6,300.
6,300. Does anybody disagree with that?
I got closer to 6,000.
Got closer to 6,000, okay. Who else got something else? 6,100. And what did you get, Mike? You said 65, okay. Now, why are those so divergent? It's where you collected it, right? You're having to fit a black body spectrum to this, and how you chose to go through the data. You don't have enough information really to tell what's absorption and what's really part of the continuum. So based on our observations, you could say, well, the temperature is around 6,300 plus or minus a couple hundred. Okay. What about B? Give me a couple values for that. 69.
I got 67.
67, okay. 68, all right, so we're still 6,700 plus or minus a couple hundred. What about C?
72.
72, and I heard 73. 76, okay. And 4? 58, 57. What'd you say? 58, okay. Anybody else have something different from that? No, so those aren't wrong answers, right? It's just showing you that based on our assumptions that there has to be a continuous spectrum in here, that you don't know enough about what is causing the absorption in order to really put a specific blackbody curve on there, so you're kind of guessing a little bit. And sometimes with the stars, the peak is not in the visible. So you have to do it all off of the tail coming out here. And that can be a challenge because you don't know where the peak is. You have to approximate. Now, if we had used a computer and we used the Planck function that's in your book, and we plotted it on top of these things and shifted it around, that would give us a much more specific answer, right? Because then the computer would take that into account. But that's not bad, to within a couple hundred degrees. All right, so now we need to know more about what these things are made out of, and that's going to help us if we do some laboratory experiments. So if you go to part B, this is the, I did not use a container of antifreeze, but I used our didymium filter. So remind me what happened when we did our didymium filter. Put the didymium, the yellow disappeared. So you get an absorption line. You got some big chunk of absorption line taken out of that, right? So we can start to talk about Kirchhoff's laws and how we determine what the spectrum is going to look like. And there's really, there's two types of situations, and one is a combination of the first two. The first one is objects that are hot and dense. What type of spectrum do they have? If you have a hot, dense object, any hot, dense object. Bright, well, it's going to be continuous, and if it's bright and if it's hot, it'll be blue. What if it's cold? Red. What if it's U? Infrared, right? So you are an HDO, hot dense object. Okay, you can put that on your resume. You know what I just realized? I left the glasses on the camera. Is that still working? Yeah, that's cool. All right. They can stay on there. We might not use this one. We'll see. All right, so hot dense objects, that's a continuous, or we sometimes call that black body. And I'd like you to take a moment when you get back to your book to look at the derivation of the black body formula. I don't really want to go through that in class because it's a lot of a lot of algebra. But if you take a look at it and look at the assumptions, I will tell you for a black body spectrum, all the assumptions that are made are you have an atom with two possible states. And those two possible states get into a statistical equilibrium that results in a continuous spectrum. Right? And there's an interesting story about that, of how that came about. Planck, it's the guy whose the function was named after, why do you think he wanted to know what the spectrum of an HDO was? He was trying to make a more efficient light bulb. Right? He didn't care about stars, he didn't care about basic physics. What he cared about is that if you want to build a light bulb, you want as much energy as possible to come out in visible light, and as minimal energy as possible to come out in other wavelengths, because you can't see those. So you want to build a light bulb where the peak of the emission is in the visible. So you can do that experimentally, right, by just putting stuff together and, you know, whoosh. And he did that, and he made spectra of light bulbs, and he knew that it didn't match any of our known physical ideas. But then he came up with the atomic theory of this thing to give us the continuous function. In fact, the quantized nature of atoms, this electron state where you've got quantized energy states, basically came out of trying to make a more efficient light bulb, which I think is cool. Okay, so a diffuse hot object, however, is going to do what? Now, diffuse and hot would be this. This is a diffuse gas, and by diffuse, all we mean is it's relatively difficult for the atoms to hit one another, so if they get excited, they don't de-excite by smacking into each other. They only de-excite through emission. Okay, so a diffuse object, what type of spectrum do we call that? Emission spectrum. And so the combination of a hot dense object and a diffuse gas that's at a slightly lower temperature, right, is called what? What type of spectrum is that? I'll give you a hint. Absorption spectrum. Yeah, it's what we were just looking at in those stars. Yeah.
Line between the defining area. Is this sort of where Fermi statistics do and don't apply?
So no, because in all cases those statistics apply. What's happening is whether or not you can get in a diffuse gas, you are only exciting and de-exciting by photons, right? So if it's diffuse, you absorb a photon, your electron goes up, and then your atom floats around for a while until the statistics probability, enough statistical time has elapsed for it to drop back down and emits a photon. Right? In a dense gas, though, you get excited by something, either getting hit by another atom or a photon, and then before you can emit another photon, you might emit a photon or you might hit another atom. And so you don't get very discrete emission lines because you are de-exciting through collisions and all sorts of other things. So in the case of a black body spectrum or a continuous spectrum, what matters is the populations of states in the atoms of the different electrons, and that's fixed by the statistics of the statistical probability of de-exciting or exciting. Right? But it's all mishmashed together because you've got to worry about the fact that you're not only emitting photons, but you're smacking into other stuff. And then the other one, the limiting factor on the hot dense, or the hot dense stuff surrounded by a diffuse gas is the temperature. Because if I take a hot dense object and surround it by a cool gas, I have unexcited atoms in the cool gas. I've got a continuous spectrum in the dense material, and so all the photons come out, but they only get absorbed by the atoms that can be excited in the diffuse material. Now, if the temperature of the diffuse material is hotter than the dense stuff, I'll get an emission line on top of the continuous, because the photons aren't getting absorbed. You've just got another gas that's giving you an emission spectrum, so you combine them together. Right? So take a minute for a second and answer these two questions, part 1 and 2, or part B, number 1 and 2, looking at our synthetic spectrum. And this is just to reemphasize the fact that this makes astronomy and astrophysics a laboratory science. Because in order to study solar spectra or stellar spectra, we need to do activity, or we need to do experiments in the laboratory. Gosh. Yes, yeah. This was the didymium filter, not the container of antifreeze, but it's the same process. All right, so tell me what are our arguments for there being iron in this simulated spectrum? Right, exactly. Now, what about all those other places where the dark spots are, but iron isn't? It's just other stuff, right? So in order to study stellar spectra, what we need to do is combine in the laboratory. We have to take a spectrum of pretty much every single atom there is. Now I want to point out something important about that, because you often think that, oh hey, physicists know quantum mechanics, right? So we can theoretically produce the spectrum of any material we want. And that is not true. Atomic spectra were pretty good, right? We can do quantum mechanical calculations to get what the atomic spectra is supposed to look like. But as soon as you get into molecular spectra, almost all of it is laboratory work where they take a material at a certain temperature and pressure, shine light through it, record the spectrum, and then put that in a database. And that's what we have to compare by. So stellar spectra is nice because most atomic spectra can be reproduced through quantum mechanical calculations, although very challenging, difficult ones. How many people were in my physics class? You remember we did Schrodinger's equation, and we had one equation for every electron, right? You had to do the superposition of all the electron quantum states. It's a mess. You can do it, but it's a mess. But when you get to molecular stuff, you're better off just building stuff in the laboratory. All right, so now the last thing I want to do here with this activity is, and this came out funny on the printer, so just turn over to the very last page. You'll see part C. And what I'm going to do here is I'm going to have you sketch a couple of these spectra that I'm going to put up. We're going to pick a bunch of spectra. We're going to do our laboratory experiments to determine what types of spectra can be seen from different gases, and then I'll see if you can reproduce some unknown spectra when I put them up there. Okay? That's the plan. So what you're going to need here is you're going to have to use your imagination a little bit. I'm going to show you a spectrum. You have to memorize it. I'm going to turn up the lights a little bit. You'll have to draw it. I can turn it back on, right? And you'll have to do this for a few of these things. So let's start with, and I'm going to tell you what these are. Let's start out with the easiest gas, which is hydrogen. Hydrogen, hydrogen. What happened to hydrogen? Oh, it's in the thing. Thank you. Okay. Are you ready? Hydrogen gas. Oh, hang on. Let me turn that off. Now, I know you can't see anything, but let's see. Can you? So what do you see? Can you describe it for me?
Darkness of my soul.
The darkness of your soul, illuminated by, I see a purple line, I see a cyan line, and I see a red line. Now this is going to be a little bit tricky. You want to make sure that you, I tried to measure these with the spectrometers we built, but it didn't work out too well, so we're just going to kind of wing it here. Use your cognitive abilities to recognize which color goes where, and see if you can draw those to scale. Okay, now you can't really see anything, so I'm going to turn on this other light. And you should be able to see both at the same time. Can you see enough to draw, or should I turn on the other light? What do you think? Hey, that works out pretty well. And you see the spectrum repeated several times. Wow. That's really crazy. You can't see that at all. Why does anybody watch reality TV? Do you know?
So what are we supposed to be running this on?
On the back, very back of your sheet of paper, you see this table, and it has the wavelengths, 400, 500, and it has the colors listed, so violet, orange, red. So try to draw that as close to those colors as you can see. And so we've got violet at about 400 nanometers, green, yellow around 500, orange, red at about 600, and deep red at about 700. So you have to make some judgment calls there about where to draw those. This is part C. It's on the very, very back. We did not skip. We did part B. That was what we just did. Part B was the absorption spectra. This back page got put on backwards when it went through the photocopier. All right. Can I put in another one? You ready? Okay. So, what should we do next? Helium? Yes? Who wants helium? All right, here we go. Here's the only second of 3 atoms in the solar system, in the universe. All right. Ooh, this one's a little complicated. A lot more lines. Now, don't forget, you only have to do the first order, which is, looks to me like it goes blue, blue, green, yellow, red, red. Blue, green, yellow, red, red. Ouch! It's hot. Did somebody just come in? Hello? Okay.
It's really funny process walking on and see all the lights off and a bunch of people sitting on the phone.
Yeah, I know. All right. Are you ready for another one? Almost. No, you're drawing neon. Oh, no. All right, I'm going to turn this off, otherwise it gets too hot and I can't. Okay. Well, you know, that's not too bad. And you can, so here's what you would do, right, is you maybe draw a bracket around all those yellow red lines and say 5 yellow red lines equally spaced. So don't feel like you've got to draw. Just be thankful I didn't bring in colored pencils like I usually do. It would be more fun, but then I'd have to have more colored pencils. Okay, you got that one? Almost. Okay, I'm going to turn that off so it doesn't get too hot for me to take another. All right. Now I'm going to show you one. This is argon. Why is it always the noble gases? Oh, can you see that one? It's a little faint. How's that? I think this lamp might be having a leak in it, but I think you can do all right. That's argon. And okay, we're going to do how many more slots do you have? Just one? Oh, you just did 4 gases. All right. Well, make some more room in there. So I'm going to do one more. Okay? Are you ready? One more. This is mercury. And why do we do mercury? Where do we use mercury lamps? Ooh, that's nice. Does anybody know where we use mercury lamps? Say it again. What? Yeah. Well, we don't. Yeah, we use them in street lamps, right? Street lamps. But yeah, and the reason we do that is because they have very strong emission in the range that's nice for nighttime lighting, but you can also filter out quite a bit of it. So if you have a telescope, you can put what's called a mercury filter that blocks out that light, so you can do some stargazing even if there happens to be street lights around. It's kind of nice. All right, got that one? Now let's do an unknown. You ready? I'm going to do an unknown one, and you have to tell me what it is. Here it comes. Are you ready? I'm tricking you. That's air. Ha! I tricked you. No, let's do another. Let's do a real one. A real unknown that you. Let's do one more. What about that one? You think? Does it look like hydrogen?
Yeah.
Yeah, it does. It's water vapor. But it looks very similar to a hydrogen spectrum, but it isn't. It's water vapor. But of course, what's probably happening is you're getting some ionized or some excited hydrogen atoms in there as well, and hydrogen makes up most of water. So that looks very much like hydrogen. Very good. Although if we were astronomers, we'd say there was hydrogen, and we'd be wrong because it was water vapor. All right, I'm going to do one more, unknown. Are you ready? Are you ready? Okay. Shh. Thought you fell asleep on me. 5, 4, 3, 2, 1. Neon. See? You've been doing this for 2 seconds, and already you can identify every gas I put up here. Or at least you can identify that you don't know what the gas is. All right, I think I've kind of run the spectrum on that. Ha ha. Get it? Spectrum. Okay. So that kind of gives the whole breakdown of what we have to work with. We can work with the continuous spectrum. What does the continuous spectrum tell us? Remind me. If it's a hot, dense object, right? And so, what is the? We can't tell how dense it is, but we can do. What can we tell about it? Its peak wavelength, and the peak wavelength is going to tell us how hot it is, right? So we can tell how hot it is with the continuous spectrum. What does the emission spectrum tell us? Tells us the composition of the atmosphere, right? Tells us what's in there of whatever we're looking at. Well, it tells us the composition of the gas, right? If it's in an atmosphere around a dense object, it's going to be an absorption spectra. The absorption spectra also tells you the composition, but it also tells you one other thing. What does it tell you? If I've got the hot, dense object and I have a diffuse gas around it, what do you know about the temperature of the diffuse gas? It's cooler, right? So you get all this information, and in fact, if you have really careful observations, you can tell the atmospheric not only composition, but temperature as a function of depth as you go down in the star or the planet or whatever you're talking about. So you can learn an awful lot by looking at galaxies, stars, planets. Not only can we tell their composition and their temperature, but we can tell their interior structure. We know the sun is a dense object surrounded by a diffuse atmosphere, right? So you can do a lot of really cool stuff like that. I just wanted to write down some of the processes that occur in all objects. And these are all related to atomic processes. And these are the processes. I've listed them up here on the board. The first one's photoexcitation. Photoexcitation happens when you photon an atom. And I can draw that. Some atom, if it gets hit by a photon, which we denote as h nu, then that becomes, the photon is absorbed, and we get an excited atom that we mark as X star. So now we have an atom in a new state. It has absorbed the photon, and it now has more energy. That can lead to the next process, which is spontaneous emission. If I have an excited atom, which is an X with a little star after it, that will go to an unexcited atom, an electron in a lower state, plus emitting a photon of exactly the same wavelength that it took for it to excite up to that level. Okay? If I happen to be in a dense object, I don't have any time to wait for spontaneous emission, so I can either collisionally excite or de-excite an atom. And that has to do with, if I have an unexcited atom, I have another atom come in with some kinetic energy, smacks into the atom, it will excite that atom, excite the electron in that atom to an energy level that has that same energy, and or change the momentum of the atom it hit. Right? Because remember, electrons can only go up by specific energy levels. If I've got more energy in the collision than I have to excite the atom, then it goes into the change in kinetic energy of the atom itself. Stimulated emission is a special case of taking an excited atom, or taking an atom, exciting it up to one level, and then hitting it with a photon that causes it to cascade, with photons coming out all at the same wavelength. And you have, how many, you still have your laser beam on you? Oh, didn't bring your laser beam. That is stimulated emission, right? Stimulated emission is our laser. And then lastly, what we talk about we don't talk too much about stimulated emission in astronomy, just because, well, there are masers in gases where you can get microwaves that are stimulated emission, but you don't often get a lot of that. But what we do see a lot of is photoionization, and that's where we take an atom and we hit it with enough energy, with a high energy photon, that it turns into an ionized atom that we write as X plus. It's not a star, that's a plus. So that means we've lost an electron to space. Now, the only way this thing can go back to its ground state with an electron is if another electron comes by and takes it away. This is going to become important because in stars, as we heat up the star, so imagine for a second if we have a star surrounded by a gas of pure hydrogen, right? If the hydrogen is cool enough, all of the hydrogen atoms are in the ground state. All the electrons in the hydrogen atom are in the ground state. As I start to heat up the gas, though, they are going to collisionally ionize themselves as we heat up the gas into a plasma where now I no longer have hydrogen atoms, I have ionized hydrogen. Will you see hydrogen absorption through an ionized hydrogen gas? No. So in very hot stars you don't see hydrogen absorption. For a long time that made us think there wasn't any hydrogen in hot stars, but that's not true. It's just the hydrogen has been ionized. Same thing with cool stars. In very, very cool stars, the hydrogen goes into molecular hydrogen. And so now you no longer get absorption of the electrons because you've got rotational and vibrational states rather than atomic states, and you lose the hydrogen absorption. So in both cool stars and hot stars, you lose the absorption from hydrogen. So we have to take into account temperature when we talk about stellar spectra, which we're going to do a lot later. All right, so questions about that? No questions? None at all? If I were to ask you some important questions about the properties of matter, what would you say? Yes. Okay. All right. So these are the processes. But this is the thing, right? In our basic physics class, we talk about what? Absorbing photons, scattering photons, reflecting photons, right? We didn't get into the specific processes. These are the atomic processes that happen in matter. If a photon is interacting with matter, one of these things is happening. Now, sometimes it's not going into electron excitation. Sometimes it's going into rotational excitation or vibrational excitation if we're talking about molecules. But it's all interaction of light and matter. All of it. So every process in the universe. Provided we're not talking about dark matter, because dark matter doesn't interact with light. Details. Okay. All right, so I do want to write down one quick thing about the hydrogen gas, because this is something that will come in handy when you start to look at spectra, and that is the various spectral lines that you see in the hydrogen spectrum. So let's go back and look at our energy level diagram for hydrogen. This is E of n, where n is equal to 1, 2, 3, 4, 5. And of course it goes like 1 over n squared, so that's the best I can do there. So the energy from the ground state is minus 13.6 electron volts. The next highest energy is going to be that divided by 2 squared. The next highest energy is going to be that divided by 4 squared, or 3 squared, 4 squared on up. These have certain names which we don't use in physics, but we do use in astronomy. If you're going from the n equals 2 to the n equals 1 state, or actually if you're going from the n equals anything equals 1 state, we call that the Lyman lines. Or Lyman alpha is the 2 to 1 state, Lyman beta is the 3 to 1 state, so on. Right, those are the lines that show up in our spectra. If you're going from the any state to the second state, those are called the Balmer lines. Those happen in the visible spectrum. Those are the first ones that were observed by Bohr. And Bohr predicted all of these other lines, which were then discovered in stars. So there was a connection at this time between the particle, or the astrophysics that was happening in space and the particle physics that was happening in the laboratory. If you're going from any state to the third state, we have the Paschen lines. And there's one other I'll add in there. There's a bunch of them. There's Pfund and Humphreys, and anyway, but if you're going to the fourth state, it's called the bracket state. And of course, this was all named because nobody knew what the heck was going on. They just said, hey, Balmer found these lines, and Lyman found these lines, and Paschen found these lines. And why were different researchers finding different lines? Because they were doing experiments at different wavelengths, right? And the apparatus needed to explore the Lyman emission lines was different than the apparatus for the Balmer emissions and whatever. So we had to eventually put all this stuff together, which we did thanks to the Bohr model of the atom and eventually quantum mechanics. All right, so that's the hydrogen atom. These are going to dominate our spectra. And if you take a minute to look at the spectra in your pamphlet here, what do you guess? There's, let's see here, there are these prominent lines, let's say in the middle one. What would you suggest those prominent lines are due to? More than likely. I'll give you a hint. What's 90% of the star's atmosphere? Hydrogen. Okay, so you can usually pick up the Balmer lines in the spectra of stars. And the nice thing about that is once you identify the Balmer lines, you can identify every other line because you have a scale of wavelength you can put it on. All right. How are we doing on time? We got about 15 minutes left. Just to recap again, what can we tell about from a continuous spectrum? Hot dense object, what the temperature is, right? This is cool. That means you can look outside and look at a star. You don't have to go anywhere. You know its temperature, right? You have spectrophotometer eyeballs. You see blue, you know it's hot. You see red, you know it's cold. Okay, and from the absorption spectra, we can tell both composition and the temperature of the layers, right? And then from an emission spectrum, you can just tell composition. And that's fine as far as it goes, but what if I want to talk about how radiation travels through material, right? If I want to talk about if I have a bunch of material and I can tell all these things from it, from these different spectral features, but I still have to, I want to know in detail how the radiation gets from one end of the material to the other and what happens to it in the meantime. We need to do a process that's known as radiative transfer. We need to understand how if I have radiation and then I put material in the way, what happens to the radiation coming out the other side. And frankly, this is probably the most important physical process that we know of because we all use it every day. Driving in the fog, you are doing radiative transfer in an optical thick medium. Right? Really important that you understand what headlights look like in fog. Because you have headlights, you've got an optically thick medium, and you have you. And if you get that wrong, you're dead. Okay, so important stuff, right? Radiative transfer. In physics, though, you know, pretty much, if you think about any physics experiment you're doing, what are you doing? You're putting light through something and looking at it on the other side. Right? And this has analogies even if we're not using light as the thing we're detecting, right? The transfer of this stuff through the material, what are the reactions? All of those interactions are going to take place, those specific interactions on the atomic level. What we'd like to do is be able to write something down on the aggregate level so we can talk a little bit more about the bulk properties of material and start to get at things like, well, how much material is there between me and that light source? What's the temperature of that material between me and my light source? Am I losing any material, any light off to the side? Right? Answer questions like that. And if we can do that kind of stuff, then we can start to do some real physics in the atmospheres of these stars and planets. So let me ask you the very basic question of radiative transfer. This is the question we're trying to answer with radiative transfer. What is the fraction of light that gets through a medium? 7%? 700? 1/7. Okay, 1/7. Yeah. What type of medium? Are we talking somebody who's a post-cognition, precognition, telekinesis? You know, post-cognition is a thing. I know what happened. It is. The people will advertise it, post-cognition. So we're not talking about that kind of medium. Medium means, you know, a slab of something, right? So if I draw a picture of that slab, let me get back to my last sheet here. If I draw a picture of that slab, I've got a slab of stuff, and this stuff can be a slab of star stuff. It can be a slab of planet. It can be a slab of anything you want. It has a cross-sectional area S, right? And it has a thickness delta X. And I've got some light coming through, and on the other side, there's going to be either the light coming through plus some change in the amount of light, or there's going to be light coming through minus some change in light, depending on whether the slab of stuff is emitting or absorbing, right? So the fraction of light that makes it through is going to be depending on what the nature of the material is, because all of those processes can occur. If I have a hot gas and I'm shining light through, then I have to get all of the hot gas's light plus the light of the stuff shining through, because there's nothing to absorb it. So we can either get absorption or emission. Typically we're talking about absorption, because almost all of the time there's some process that scatters light out of the way or absorbs it or something. But if you are emitting light in the material, you have to take that into account. So let's deal with absorption for the time being, just because it makes it a little bit easier to think about. If we imagine this stuff has one atom in it that can absorb some of the incoming light. So we've got one atom inside of that can absorb incoming light. That atom is going to have a cross-sectional probability of interacting with the light. So we call that sigma. That's the cross-section of interaction. What are the units of that? Anybody know? Cross-sectional, right? Cross-section of interaction. It's a probability of impact. No, probability can have like if you think of probability densities, you can have, so the cross-sectional, we typically talk about it as the cross-sectional area, right?
Radian per meter squared?
Per meter squared, right? Or it's, well, I'm sorry, the cross-section it's a cross-sectional area. So think about it this way. Let's say I've got an atom, right? And this atom we know there's some probability that it will interact with the light that's coming in. The bigger the probability, the more likely it's going to interact with the atom, which means the closer the light is to the atom, the more likely it's going to interact. So we write it down as a cross-sectional area. Right? So if I've got the area coming in, and now it's not the area of the atom, because the atom is fluffy, but it has a cross-sectional area that depends on the probability of the interaction. So if you've got a large probability of interaction, the cross-sectional area is bigger. It's not a physical area, but it's written down in units of area. So this has units of area. And if there's only one atom in there, then I know that the change in the amount of light coming out divided by the light coming in is just going to be equal to, if I'm talking about a decrease in light, minus the cross-sectional area divided by the total area of the slab. And if we were thinking about this classically, you could think about, well, here's my slab that has an atom in it that has some size. That size has a cross-sectional area written in centimeters squared or meters squared or whatever you want to talk about. And so if I've got light coming in here, it just goes through. If I have light coming in here, it gets blocked. We know that's not really what's happening because the atom is a probabilistic fluffy little thing, but for the sake of argument, we can write it down like that. So depending on the probability of interaction, the atom has some fractional area in which, if the light goes through, it will interact. But there isn't just one particle, right? How many particles are there? 50, right? So n equals 50. There's n particles in this box, and we draw them all in here. And so that means that there's a higher chance of this thing getting absorbed. So we can write down that the total number, which could be 50, is equal to the number density, little n, times the cross-sectional area of the whole thing, x. Because S times delta x is the volume of this box. N is the number of particles per volume. If you select appropriate values, you will get 50. Right? But we get n as the total value. And so through this whole thing, the amount of light that's going to get absorbed is just going to be minus n sigma over S. Okay, with S delta x sigma over S. The nice thing about that is my cross-sectional areas cancel, because I didn't know what I was talking about anyway, in terms of whether I was talking about a star or a mouse. So it doesn't matter, right? This is generic for any type of material. But now I have a differential equation, right? I've got delta I over I is equal to minus the number density per cubic meter times sigma times delta x. This is a differential equation because if I take this in the limit, the delta x goes to some infinitesimal value, dx, right? That means that this is di, the little bit of light making it through, divided by the total light coming in, is equal to minus n sigma dx, and I can integrate both sides of that thing to figure out how much total light is absorbed or emitted from the slab based on how much light I'm putting in. Now, what are the limits of integration on this?
Well, you have to measure the total intensity of the light rays.
Right, so the total intensity to start with is going to be I naught, and that's going to, what winds up on the other side is going to be I. Could be greater or larger, but we're just going to say it's I. And on the other side, what are our limits of integration? Slab starts at, yep, 0 to x, okay? And everybody knows what the solution to this differential equation is?
It's I equals e to the minus star.
Yeah, so this side's easy, right? This is just minus n sigma x, right? Did I do that right? Yeah. This side, though, is ln of I over I naught, right? Okay. So those are equal to each other. And so if I take the natural log of both sides, there's a constant out here that we're kind of ignoring because we can measure that if we need to. And, right, we have our limits here. So the constant is determined by our limits, right? So in this case, that's going to go to 0 because we've got this completely defined. So this whole thing, if I take the natural log, or take both sides to e, then this becomes I of x is equal to I naught e to the minus n sigma x. And that is sort of a generic feature of absorbing materials, right? Because if I send in I, I'm going to get I naught out, or sorry, if I send in I naught, I'm going to get I out diminished by an exponential. And that exponential is going to depend on how much stuff I have, which is the number density, and it's going to depend on the cross-sectional area of the material. Now the cool thing about this is I can measure sigma in the laboratory. I can take a tube of hydrogen and shine light through one side of it and figure out what the probability of interaction is for that. I can do that in the laboratory. And so if I can measure how much intensity is coming out, if I know how much intensity is going in, I can figure out what the number density is. So this is how you can measure the number density of molecular clouds that are located 100,000 light years away.
So is this only valid for transmitted media, or would you just say sigma is 0 for a reflective surface?
Yeah, so this, so sigma for, well, let me put it this way. What we're leaving out of this is any source of emission from the slab. Yeah. Okay, so that would change effectively that we could have another material out here. It's usually called the source function, which would add radiation. But we'd have to include that in to this equation up here. So it would change our integral a little bit because we wouldn't just have absorption, we would also have a source term, say plus S nu for some spectrum is coming out of this thing, right? And so we could include that, and then you would wind up with two terms. The thing that's taking it out, that's going to be exponential, and the stuff that's putting it in, which depends on how it's being put in. Is it continuous? Is it emission? Right, what's happening. So this is good for any gas that you're ignoring the contribution of the spectrum itself. So if I have a molecular cloud, it's going to have emission lines. I ignore the emission lines because I just care about the star on the other side. How much is that star attenuated? And if I know the type of star, and I can measure the attenuation, then I know what the material cross-section and number density is. Right? Now, unfortunately, in astronomy, you usually don't get the number density, you usually get the column density because you don't know how thick the slab is. You don't know delta X. But at least it tells you the number density, and that gives you kind of a proxy for the total density of material. All right, so I think we're just about out of time. Let's go ahead and stop there, and we'll meet over in 240 next week. Would it be useful for these things to be archived?
Yeah.
I don't know if we'll ever do this again like this. I might try using my iPad though, but we'll see.
Do you want us to turn these papers in?
Yes, please turn these papers in. What you've done, I'm not going to worry too much about we didn't get to the last part. Oh, you know what though?
I did the last one.
What I'd like you to do, who has not done the last part? Take this home, do the last part, and bring it in on Tuesday. Oh, can we talk for a second? Just 2 minutes? So next week is our exam, right? I would like to do a take-home exam. Would that be all right? If I give it to you on Thursday, due on Tuesday. And the way this exam is going to work is I'm going to give you 5 questions of different point values. 20% of the exam is on how well it's presented. 20 points. 20 points of the exam is on how well you explain your answers. And the other 60 points come from the correctness of the answers to the take-home questions. And you can select any of those questions up to a total of 60 points. How does that sound? Does that sound all right? And I'll give you a hint. One of the questions is worth a lot of points. And the other ones, you can add up to 60. So,
if we do all the questions, do you just ignore the questions?
So I'll grade everything you turn in, but your maximum score is fixed at 100.
Okay.
But if you do all the questions and you get 190 points, then yeah, you get 100 for sure.
Okay.
Yeah. But yeah, if you want to do all of them, I think that's great. But if you don't want to do one, you don't have to.
Sounds good.
All right. We'll try it. I've never done this before, so there's a lot of things I haven't done before that we're doing. Thank you very much. Did you get your name on here, Nate? Oh, yes. Okay. Thank you, Nate. Let me save this guy.